So our perforated plate or sieve tray extraction towers are similar to sieve trays that are also used and employed in distillation and gas absorption. The tray holes here ranges from 0.32 to 0.64 centimeters in diameter, so very small for the tray holes. And the total open tray area should only be 15 to 25% of the entire tray area, meaning the open tray area, that is the sum of all the areas of your holes, should not be exceeding 25% of the total tray area. Now, the tray spacing, that is one above and under each other, should not be also beyond 25 centimeter or should not be less than 10 centimeters. So the range of the tray spacing value is given here, that is 10 to 25 centimeters. Now, for the fractional efficiency of these tray towers or sieve tray extraction towers, you have the formula, which is empirical in nature, dependent on the tray spacing, and the unit should be feet in this case if you're going to substitute in this formula. The hole diameter should also be in feet, that is the tray holes, the diameter of the holes. Then you have the sigma, the interfacial tension, which should be in dyne per centimeter. And take note that since this is empirical, there's no need for you to make your units agree. Since you see here, the units are in feet and feet per second, doesn't follow that you are to change here the dyne per centimeter into pound mass feet per hour squared. It has to be as is because, as I've said, the formula is in empirical. So whatever are the stipulated units of your variables, that should be followed. So in the case of our velocities, linear velocity, that should be in feet per second. Now, in this case, even if it's not feet per second, since the units are still anyway going to cancel each other, even if this is in meters per second, if you're going to convert to feet per second, the same conversion will be done on the other value. So there's no need for you to convert in the case of the VD and the VC. And that is the velocity of the dispersed and the continuous phases. As I've said, because they are in ratio form. So whatever conversion would happen to one, that would be same conversion that would happen to another. So there's no need for conversion in here. So we just have to take note of the specified units for the tray spacing, for the hole diameter, and for the interfacial tension. Now, problems concerning efficiencies of sieve-tray extraction towers are very straightforward. So what I mean with that is you only have to substitute to a particular formula. Now our perforated plate or sieve-tray extraction tower would look something like this. So our feed, which is the continuous phase, is introduced on top of the column and the solvent is being dispersed, flowing countercurrent to the feed that is going up, going down. So the extract is withdrawn on top of the column and your raffinate is withdrawn at the bottom of the column. So this has a high capacity of 30 to 50 cubic meter per square meter per hour, a good efficiency due to minimum back mixing, so it's efficient. And multiple interfaces can be, however, a problem here because of the dispersion of the solvent in here and of the feed that is going down. So there might be the evolution or the formation of multiple interfaces. Now, it has limited turn down feasibility, meaning it can only process a certain amount of material and can also like in the terms of the product that is being withdrawn, which is the extract, the main product, it's also very limited. So we cannot have it perform higher than the packed tray column. Now, affected by changes in wetting characteristics. So its efficiency or performance is affected by changes in wetting characteristics. The capacity that is of the solvent that is dispersed upwards countercurrent against the liquid that flows down to make sure that the feed is flowing countercurrent to it and is completely wetted by this particular solvent, which is also liquid. Limited as to which phase can be dispersed. So in the case of the sieve tray column, we cannot, just like if you recall our problem in the flooding problem for extraction tower, we cannot interchange the continuous phase to the dispersed phase, or the dispersed phase to the continuous phase. Whatever is the designed dispersed phase, that should be our dispersed phase. In this case, it should really be the solvent. So we cannot make our feed be the dispersed phase being introduced on top and the solvent being the continuous phase. And that is in the case of the sieve-tray tower. So we cannot do switching of the phases. I mean, referring to the continuous and the dispersed phases. Now, here's a sample problem where we can apply the efficiency formula that was discussed in the last two slides. So an organic solvent is extracting an acid from a water solution in a perforated tray tower. So the dispersed organic solvent, so the solvent is dispersed, this must be then the only design for the column at a rate of 600 cubic feet per hour, and the continuous aqueous flow rate referring to the feed is 400 cubic feet per hour. The interfacial tension is 15 dyne per centimeter, and the tray spacing is 1.1 feet, and the hole size on the tray is zero point 0.4 centimeters. So estimate the tray efficiency is above. And then there's a question, what would happen if the solvent rate is reduced in this particular scenario for our uh, perforated tray column. So I will stop sharing here and let's see how we're going to do about finding the unknown of this particular problem. So we will write our given for this problem. Sorry guys. Can you see the Jamboard?
Yes, miss.
Okay. So we'll
Yes, miss.
so we will have the, I just have this too high. So we'll write down the given here. So I'll just go back on the PowerPoint slide. I will not share it anymore to save us time. So I'll just pick the given information. So from the first statement, it's simply telling you that you're using an organic solvent to take away the acid from water. And your tower for this is a perforated tray tower. And that's in the first statement. In the second statement, you're given the flow rate of the dispersed phase, which is 600, and for the continuous phase, which is 400. In this case now, I'll go back to that. So your BD and VC is given 600 for the dispersed phase, cubic feet per hour, and you have 400 for the continuous phase. Take note that the flow rates that are given are volumetric flow rates, not linear velocity that is given in the formula. The interfacial tension is 15 dyne per centimeter. So this is 15 dyne per centimeter. You have the tray spacing as 1.1. So it's defined in the formula as capital letter T. So it's 1.1 centimeter. Or was it centimeter? Let me see. Oh, it's feet. The whole size is 0.40 centimeters. So this must be referring to the diameter. So the whole size is 0.3 centimeter. 0.4 rather centimeter. So we have to change this one. The unit for this is in feet. Okay. So let's see if we still have anything to add here. So interfacial tension is 15 dyne per centimeter. Tray spacing is 1.1 feet. And the hole size is 40 centimeter. We estimate the tray efficiency and what happens if the solvent flow rate is reduced. So we will have to determine in this case the E sub O. And what will happen if solvent is reduced, that is if BD is reduced, what will happen to your E sub O? It's still referring to the E sub O. If this is reduced, what will happen to the E sub O that is computed? So we will write our solution next to this by of course starting with the formula to use. So the formula to use in this case, I'll check from the PowerPoint. EO 0.32, 0.352. Let me check. Okay. So your overall tray efficiency is equal to 0.352 T raised to zero point 0.5. And then we have here the ratio of the VD to VC, which is to be raised to 0.42. All of this will be divided by the interfacial tension, the tray hole diameter raised to 0.35. And this is our formula. So if we will just simply substitute everything, actually it's just substitution to everything. So you have 0.352. The tray spacing based on what is stipulated in the problem should be in feet, or based on what is to be used in the formula is in feet. So ours is in feet already, so we can just simply place this at 1.5 raised to zero point 0.5. Now, if you notice, your flow rates are volumetric flow rates. So if you're going to look for a conversion that will change volumetric flow rates to linear velocity, that would simply be the area. And since we're referring to the same column, then there's no need to do the conversion, because what you do with the first, you also do with the second. So you'll simply use the raw value of the volumetric flow rates. So your VD is 600. We divide that by 400 and we raise that to 0.42. Your sigma is in dyne per centimeter, and there's no need for us to convert because that's what the empirical formula dictates in terms of the unit. Our diameter for the tray hole is in centimeters. In terms of the empirical formula, the diameter should be in feet. So this is where we're going to convert. So your centimeters, this would be your zero point 0.4 centimeters. We divide by 2.54 centimeters in 1 inch. So this would already be in inches. Then we'll have 1 foot having 12 inches. Now the entire expression should be multiplied, or rather raised to 0.35. So we convert the centimeters to inches by dividing it by 2.54. The inch unit here will be converted to foot or feet. And then the resulting value will be raised to 0.35. This will give us a value for the tray spacing of, let's So we have a 0.352. We multiply to 1.1 raised to zero point 0.5. We multiply to 600 divided by 400 raised to 0.42. Then we divide by 15, and then we divide by quantity. 0.4 divided by 2.54 times divided by 12 raised to 0.35. So in this case, your answer will be a 0.201. Let's see. That's it. Okay, is that the answer you're getting also for the tray space, for the overall tray efficiency?
Point 133, miss.
Zero point 0.4 divided
Sorry,
by
nag-vibrate.
2.54
Baka ako.
divided by 12, you raise to 0.35, you multiply by 15, that should be in the denominator, times 0.352 times 1.1 raised to zero point 0.5 times 600 divided by 400 raised to 0.42, 0.13. Where is the something wrong with that? 0.352 t raised to zero point 0.5. Okay, 0.113 because I changed the trace spacing in this case. The original trace spacing in the problem is just 1 foot, so I changed it to 1.1. So our answer should be 0.133. So that's correct. So this is 0.133 for our tray efficiency, overall tray efficiency. If you're going to look at it, that's very low. That is why in the case of towers or columns, even in gas absorption, the pack tower is always preferred over the tray tower. But there are applications wherein fouling is something to be considered, and if you're using packing material, the pack tower is not preferred over the tray tower because of the problem of fouling in the presence of packing material. So there is the reason why tray towers are still being used. So this is the case of the problem that we solve wherein we want to determine the overall tray efficiency for our perforated tray tower. So I'll stop sharing here and go back to our slide. Okay, so that's in the case of our overall tray efficiency for the Sieve-tray tower. Now we go to the pulse tower. So it has a reasonable, uh, sorry, it has a reasonable efficient capacity, and that's 20 to 30 cubic meter per meter squared per hour. It's best suited for nuclear applications. So when we're discussing specific types of equipments, please have emphasis on knowing their specific application or what's unique about that particular equipment. In this case, we're talking about the pulse tower. So, suited for nuclear applications due to the lack of seal, meaning this is not using any sealing material. Suited also for corrosive applications when constructed out of non-metals. It can be constructed out of non-metals. So limited stages due to back mixing, so we can have so many stages in this tower, and limited diameter and height due to the pulse energy required. So that is in the case of our pulse tower. Now, for the pulse packed and sieve-tray towers, so these are actually towers that are mechanically agitated to increase mass transfer efficiency. They are mechanically agitated. So there is some form of agitation inside the column to increase mass transfer efficiency, which is referring to the throughput. The amount of solute that gets transferred to the solvent is the mass transfer efficiency of this particular uh, extraction equipment. So for pulse pack towers, reduces HETS by a factor of 2 or so, meaning it reduces or decreases the value of the height equivalent to one theoretical stage by a factor of 2 or more. For liquids with high interfacial tension, this is also suitable, and that is, take note, the interfacial tension is already beyond the 25 that is specified for the design to address flooding. So this one is okay for 30 to 40 dyne per centimeter interfacial tension. So referring to the pulse back tower. What about the sieve-tray towers, which is also pulsed? So those are all pulsed tower. One is packed, the other one is tray towers. So this one should have a hole size only of 0.32 centimeters and a free space of 20 to 25% of the tray area. The spacing of the tray should not be uh, other than 5.1 centimeter because we're not given here a range of values. So it has to be this particular value. Trays occupy the entire cross section of the tower and there are no downspouts. So in this case, we don't have downspouts which guides the flow of the feed or the continuous phase down the column. Now we have the Shibiel tower. It's mechanically agitated also, and the agitation is in this form inside the column. So uses rotating turbine agitators with outer settling zone. So operates in a series of mixer settler extraction units and has a good actually reasonable capacity of 15 to 25 cubic meter per square meter per hour. It has high efficiency due to internal buffering. So take note, your Shibble tower has high efficiency. A good turn down capability, that's 25%, and is best suited when many stages are required. So the opposite of the other towers that we have discussed in the previous slide. Those have limited number of stages. This one does not have any. This can have many stages. So not recommended though for highly fouling systems or systems that tend to emulsify. And that is in the case of colloidal systems. So they easily emulsify and the contents of the towers gets highly fouled up. So this is not recommended. Our mechanically agitated tower, which is the civil tower. Now we also have the car reciprocating plate tower. So this is how the plates are moving. So tray holes here is 1.4 centimeters in size. Open space is increased from 25% in the ordinary sieve tray tower to 50 to 60% of the tray area. Blade spacing also is increased to as much as 15 centimeters. Highest capacity for all extraction towers, so this is worth noting, 30 to 60 cubic meter per meter squared per hour. A good efficiency, a good turn down capability of 25%, uniform shear mixing, and best suited for systems that emulsify. So the Shibil tower is not suited for those that emulsify. This one is. So if one can't be used, then we have an alternative. Now we go to multi-stage countercurrent extraction. So we have in this case several extraction units arranged in series. So our feed is introduced here, our solvent is introduced on the last stage. If we're going to rotate this entire schematic uh, clockwise, that is clockwise, we will have a tower wherein the feed is introduced on top, the solvent is still introduced at the bottom of that tower. Okay, our overall material balance is basically in principle the same as the other unit operations equipment. We add the streams that enters and we equate that to the sum of the streams that leave our equipment, and that would be corresponding to the bulk phase. Now, the pattern that we carry on based on making a balance on the solute is the overall material balance equation. What we do with each of the phases there, we multiply it with the corresponding mass fraction of the corresponding phases. So LO will be multiplied to XCO, V will be multiplied to YC, and then the other L and V's here will be multiplied also to the X and the Y. So X for the feed concentration and the raffinate concentration, and Y for the extra concentration and the solvent concentration. Okay, our solvent is V and our extract is also V. Our feed is L and our raffinate is L. This is our bulk phase M. uh, if we do if we do rather solutions based on graphical approach, so we will have to construct the line LO and V sub n plus 1, where LO is your feed and V sub n plus 1 is the solvent. Somewhere in between these points, which we connected, is the bulk phase M, which we can locate as what was taught to you using either inverse lever arm rule or material balance. So you can use inverse lever arm rule or material balance. Then, upon locating the M, we can determine the uh, values or the location rather of the extract and the raffinate by trial and error. So you have a rectangular diagram below wherein you can assign a point here for the raffinate. You go down, you turn right, you go up, and then connect. Once you connect the two and it passes right on M, then this would be your equilibrated phases, which is your V1 and Ln. Oh, I'm sorry, class. This is not the way you do it, by the way. Sorry. What should be equilibrated, rather, sorry. What should be equilibrated is the V1 and the L1, and it's not shown here, and it's a graphical thing. So if you have V1 here, you have L1, you look for the L1, and then you connect it with the V1. So we will do that graphically, and it is not something that we will now be concentrating on, because I want us to concentrate on the analytical approach of finding the number of stages. So erase what I said. We're in V1 and L sub n are equilibrated. They're not equilibrated. What is equilibrated is V1 and L1. And that's something for you to just study, because that is relying on graphical approach. Now, this is a sample problem which we will solve, that in 2 minutes I will be disconnected, so we will just reconnect. Okay, I will just write down the given for this problem so we can save time later on. So an aqueous feed of 200 kilograms per hour containing 25 weight percent acetic acid is being extracted by using pure isopropyl ether at the rate of 600 kilogram per hour in a countercurrent multistage system. The exit acid concentration in the aqueous phase, this is referring to the raffinate phase, is to contain 3 weight percent acetic acid. Calculate the compositions and the amounts of the extract of the exit extract and raffinate streams. Now, this problem, class, cannot be purely solved using analytical approach. It would be both relying on graphical and analytical approach. But nonetheless, we can do the computation here with a little of the graphical part. But we will not solve later on the number of stages using, or we will not determine the number of stages using graphical approach. We will use the Krimser equation, which is purely analytical. So we will go back to the board that we have. So stop sharing here, and we will write down our given information. So if I'll be cut, we'll use the same link as I have mentioned a while ago. So this is our next problem. So the given for this problem, I will just not anymore show the slide. So it's 25 weight percent acetic acid for a feed. So in that case, if it's feed having